Hi everybody, welcome back to the Feynman technique. So today we're going to be solving this, and we're not actually going to be using Feynman integration today. However, we are going to be using two formulas that we derived in earlier videos, and those formulas were derived with Feynman integration, so this counts. And by the way, for my next video, I may show the quote-unquote standard Feynman integration way to solve this. But I like this way I'm about to show. Um, just because it follows from the videos that we've already been doing, and we can apply those results to this problem. So let's get started. So the first thing we're going to be using is tool number one, and it's this formula right here. Any integral of this form evaluates to exactly this. All right, and the next tool we're going to be using is this. Again, we already derived both of these formulas on this channel using Feynman integration. All right, so those are our two tools. They're right here for future reference. So the next identity that we want to use, or the next fact that we're just going to state outright here, is that this is true, and this is just a simple evaluation of this integral. We really should have written it the other way around. But anyway, if you evaluate that integral, you get 1 over a. All right. And that, of course, assumes a is positive. All right. So if we let a equal x squared plus 1, we can see that x squared plus 1 is equal to this integral, which we will plug in to our original I. So now we have I represented as an integral within an integral. It's a double integral here. All right. And then we can use exponent laws to separate this into the product of two exponentials. All right, and then we plug that modified form back into our integral. And then we notice that since we're integrating with respect to t on the inside, the terms with only x are constants. And we group it like this. And then next, we can use Fubini's theorem to swap the order of integration. So the outer integral becomes dt, and the inner becomes dx. All right. And now we have our inner integral that looks like this. And this is in the form of our first tool right here. Except in our tool, we have e to the negative b squared x squared. And in our inner integral right here, we have e to the negative tx squared. Well, that implies that we should set b equal to square root of t when we apply the formula. Okay, so that means that the result of that inner integral is just pi over 2. Well, it's this. I'm not going to explicitly state what that is. All right, so now our original integral has transformed into this. And we can pull out that square root of pi over 2. All right, so now we have our integral in this form after we combine the exponential terms. Okay, so this is looking kind of like, if we go back here, this is looking kind of like our second form. Kind of. Except we have that annoying square root of t in the denominator. But what we can do in this integral right here is let t equal to something squared, u squared. All right, so we're going to let t equal u squared. Therefore, our square root of t is u, and our dt is just 2u du. Putting that back in, and now we have this, and this is much closer to our form. In fact, it matches our form exactly after simplification. You'll notice the u and the u cancel out, and also the 2 and the 2 cancel out. So we are left with just this integral right here, and this is in the form that we can plug into formula number 2 right here. All right, but in our tool, we have this, and in ours, we have this. So we need a squared to equal 1, which means that a is equal to 1, and we need b squared to equal a squared over 4, meaning b is a over 2. So we plug that into our formula, and our integral value is just this. But don't forget, we need to multiply that by the square root of pi, and finally we have our answer. This is probably familiar to those of you watching this channel. You've probably seen it derived the other way, where you differentiate under the integral sign twice and create a differential equation. But I like this method. I've not seen this way before. And I hope you enjoyed that, and we'll see you next time.